The silence after us, asterisk, imagine waking up in a world where you are the last human being alive. The sun rises, as it always has, golden, silent, indifferent. The wind stirs the leaves, birds call out their morning songs, and the ocean rolls in, with its eternal rhythm. But no one answers your voice. There are no footsteps echoing down the hallways, no distant hum of traffic, no laughter, no music, no voices, just silence. You walk through the empty streets of a once bustling city. The lights are still on in some buildings, powered by forgotten generators. Dust has begun to settle on the keyboards of abandoned computers. A coffee cup sits half-finished on a desk, long since gone cold. Nature is already reclaiming the edges. Vines curling through broken windows, moss creeping up concrete walls. And then it hits you. You are completely, utterly alone. This is not science fiction. This is not the opening scene of a dystopian movie. This is a real possibility, one that, while distant, is not beyond the realm of scientific plausibility. The extinction of Homo sapiens is not only possible in the grand scale of geological time, it is statistically inevitable. Let's take a moment to breathe. Let's let that thought settle, not with fear, but with curiosity. The cosmic context of extinction. To understand the fragility of our existence, we must first understand the scale of time and space in which we live. The Earth is approximately 4.5 billion years old. Life has existed here for at least 3.8 billion years, evolving from single-celled organisms into the vast diversity we see today. Yet, of all the species that have ever lived, it is estimated that over 99% are now extinct. Extinction is not an anomaly, it is the rule. There have been 5 major mass extinction events in Earth's history, each wiping out a significant portion of life on the planet. The most famous is the Cretaceous Speleogene extinction, which eliminated the non-avian dinosaurs around 66 million years ago. This was caused by a combination of volcanic activity and an asteroid impact, a reminder that life is vulnerable to both slow, creeping changes and sudden, catastrophic events. Homo sapiens have only existed for about 300,000 years, a blink of an eye in cosmic terms. We are a relatively new species, still young, still adapting, still expanding. But just like the trilobites, the ammonites, and the dinosaurs before us, we too could one day vanish from the fossil record. The statistical likelihood of human extinction from a purely statistical standpoint, the idea that humans will exist forever, is unrealistic. In fact, most species do not last more than a few million years. Given that we've only been around for a fraction of that time, it's reasonable to assume that we, too, will eventually go extinct, unless we actively prevent it. In 2016, philosopher Toby Ord published a paper estimating the probability of human extinction within the next century. While the exact numbers are debated, his conclusion was sobering. The risk, while low, is not negligible, especially when considering emerging technologies like artificial intelligence, synthetic biology, and climate change. Moreover, the universe itself is not a safe place. Asteroids, gamma-ray bursts, nearby supernova, these are cosmic threats that could end life on Earth without warning. While the probability of such an event occurring in the near future is small over long enough timescales, the likelihood becomes almost certain. Even if we manage to avoid these external threats, internal ones remain. History has shown that civilizations rise and fall, empires collapse, societies fracture. We are not immune to the same patterns that have repeated across time. The psychological impact of imagining Our end. Why does the idea of human extinction feel so unsettling? It's not just the loss of life, it's the erasure of meaning. Our identities, our cultures, our histories, all of it built on the assumption that someone, someday, will remember us. But what if no one does? The thought of a world without humans is not just about the end of us. It's about the end of everything we know. The end of music, of poetry, of science, of love. The end of every joke ever told, every story ever written, every dream ever dreamed. And yet, the universe will not mourn. The stars will still burn. The galaxies will still spin. The laws of physics will remain unchanged. In the grand cosmic narrative, we are but a fleeting moment. This is not meant to depress you. It is meant to awaken a sense of awe, and perhaps a sense of peace, because, in the face of such vastness, the fact that we are here at all is a miracle. The philosophical implications of our impermanence, we are destined to vanish. Does anything we do matter? This is the central philosophical question that underlies all discussions of extinction. It's a question that has haunted thinkers for centuries. Existentialists like Albert Camus and Jean-Paul Sartre grappled with the absurdity of existence. The idea that life has no inherent meaning and that we must create our own in that light. The potential extinction of humanity does not erase meaning. It simply reminds us that meaning is something we choose to give. Some find meaning in legacy, in the idea that our actions will ripple forward through time. Others find meaning in the present, in the joy of connection, the beauty of the moment, the richness of experience, and some find meaning in the very act of confronting the void, of staring into the abyss and not looking away. There is a strange comfort in realizing that everything ends. It makes the time we have more precious. It makes every sunrise more beautiful, every conversation more meaningful, every breath more sacred. The scientific possibility of surviving beyond Earth, of course. Extinction is not the only path forward. Some scientists and futurists believe that humanity may one day escape Earth, colonizing Mars, building space habitats, or even traveling to other star systems. Projects like SpaceX's Starship, NASA's Artemis program, and initiatives like Breakthrough Starshot are all steps toward that goal. The idea is not science fiction, it is a matter of time, resources, and willpower. But even if we do become a multiplanetary species, we are still not immune to extinction. The universe is vast and indifferent. The same forces that could wipe us out on Earth could follow us to Mars, to the Moon, or to the stars. Moreover, the further we spread, the more we risk becoming something unrecognizable, a theme we will explore in later segments. For now, let us simply consider the possibility that we may never leave Earth, that this planet, with all its beauty and chaos, is the only home we will ever know. The quiet aftermath. Let's return to that opening image, the world after us. In this imagined future, nature flourishes. Forests reclaim cities. Rivers carve new paths through forgotten streets. Animals move freely through the ruins of human civilization. The air clears. The oceans recover. Life continues, and yet there is no one to witness it. This is not a tragedy, not in the way we usually define it. There is no suffering, no grief, no mourning. It is simply silence, a silence that is, in its own way, peaceful, because extinction is not the end of the world, it is the end of our world. But the Earth will endure, the stars will continue to shine, and perhaps, somewhere, another species will rise, curious, intelligent, fragile, and wonder if they were ever truly alone. Final thoughts as we conclude this first segment. I invite you to sit with these thoughts. Let your mind wander through the vast corridors of time. Imagine the rise and fall of civilizations, the birth and death of stars, the endless cycle of life and extinction, and then, gently, let it all go. Because the beauty of being here now is that we get to ask these questions at all. So breathe, let your thoughts drift like clouds across a darkening sky. And as the silence settles in, let it carry you into sleep. The Fermi Paradox. Where is everybody? Let's begin with a question that has haunted scientists, philosophers, and dreamers alike for decades. Where is everybody? It's a deceptively simple question, and yet it cuts to the heart of one of the most profound mysteries in science, the Fermi Paradox. Consider this. Our galaxy alone contains an estimated 100 to 400 billion stars, and the observable universe, it holds at least 2 trillion galaxies. That means there are more stars in the cosmos than grains of sand on all the beaches of Earth. And yet, as we look out into the vastness of space, we see no signs of intelligent life, no signals, no messages, no spacecraft, no evidence that we are not alone. This contradiction between the high probability of alien civilizations and the complete absence of any observable evidence is what we call the Fermi Paradox. It was named after the physicist Enrico Fermi, who famously posed the question during a casual lunchtime conversation in 1950. He was surrounded by some of the greatest minds of his time, scientists who understood the sheer scale of the universe and the likelihood that life could arise elsewhere. So why, Fermi asked, haven't we seen any sign of them? It's a question that still lingers unanswered. In the silence of the cosmos, the numbers suggest we shouldn't be alone. Let's start with the numbers. The Milky Way is about 13.5 billion years old. Our Sun, by comparison, is only 4.6 billion years old. That means there have been billions of years and billions of stars for life to emerge before Earth even existed. Many of those stars are orbited by planets. In fact, thanks to missions like NASA's Kepler Space Telescope and the Transiting Exoplanet Survey satellite TESS, we now know that planets are incredibly common in the galaxy. It's estimated that nearly every star hosts at least one planet, and many of those are in the so-called habitable zone, where conditions might allow for liquid water and potentially life. If even a tiny fraction of those planets develop life, and an even tinier fraction develop intelligent, technological life, then the math suggests there should be thousands, perhaps millions, of civilizations in our galaxy alone. Given that some of these civilizations could be millions of years older than us, with technology far beyond our comprehension, it seems logical that they should have made their presence known by now. And yet, the sky remains silent. The great silence, this silence is what makes the Fermi Paradox so unsettling. If intelligent life is common, and if interstellar travel is even theoretically possible, then why haven't we seen any evidence of alien visitors, probes, or radio signals? Why have we not received a single message from across the stars? This is what astrophysicist David Brin called the Great Silence, a cosmic void that defies expectation. Consider this. If a single civilization developed the ability to send self-replicating probes, machines that could travel to nearby star systems, build copies of themselves, and continue outward, then, in just a few million years, they could have explored or colonized the entire galaxy. A few million years may sound like a long time, but on a cosmic scale, it's a blink of an eye. The Milky Way is over 13 billion years old. There has been plenty of time for such a process to unfold multiple times over, and yet we see no sign of alien probes, no Dyson spheres encircling stars, no massive structures built by advanced civilizations, no artificial radio signals, just silence. The Drake equation, a framework for the unknown to better understand the paradox. We turn to the Drake equation, a formula proposed by astronomer Frank Drake in 1961 as a way to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. The equation is n equals r asterisk times f p times n times f l times phi times fc times l, where n is the number of civilizations in our galaxy with which communication might be possible. R asterisk is the average rate of star formation in our galaxy. Fp is the fraction of those stars that have planetary systems. Ni is the average number of planets that can potentially support life. Per star that has planets. Fl is the fraction of those planets that actually develop life. Phi is the fraction of life-bearing planets that develop intelligent life. Fc is the fraction of civilizations that develop technology that releases detectable signs of their existence into space. L is the length of time such civilizations release detectable signals into space. The problem is that we don't know most of these values with any certainty. Some are based on observation, others are pure guesswork. But even with optimistic estimates, the equation suggests there should be dozens, perhaps hundreds, of civilizations in our galaxy right now, and yet we find nothing. Possible explanations, the great filter, one of the most chilling explanations. For the Fermi Paradox is the idea of the great filter, a barrier so difficult to overcome that it prevents life from progressing to the point of interstellar communication or travel. The question is, where is the filter? Is it behind us, meaning that the emergence of intelligent life is extremely rare? Or is it ahead of us, suggesting that most civilizations reach a certain point and then destroy themselves? If the filter is behind us, then we are among the lucky few who made it through. Perhaps the origin of life itself is extraordinarily rare. Or maybe the jump from simple cells to complex organisms, or from complex organisms to intelligent life is so improbable that it has only happened once here on Earth. But if the filter is ahead of us, then we are in danger. It suggests that civilizations tend to collapse, not from external threats, but from internal ones. Climate change, nuclear war, runaway artificial intelligence, biotechnology gone wrong. Any of these could be the universal bottleneck that prevents civilizations from surviving long enough to make contact. If that's the case, then the silence of the universe is not just an absence, it's a warning. The zoo hypothesis and other speculative explanations. There are, of course, other possible explanations, some more speculative than others. One idea is the zoo hypothesis, which suggests that advanced civilizations are aware of us, but choose not to interfere, much like how we might observe animals in a zoo without making contact. Another is the planetarium hypothesis, which proposes that we might be living in a simulated reality, a kind of cosmic experiment or observation chamber, and that the apparent emptiness of the universe is part of the illusion. There's also the dark forest hypothesis, popularized by Chinese science fiction author Liu Cixin. It suggests that the universe is a dangerous place, and that civilizations hide their existence to avoid being destroyed by more advanced species. In this view, the silence is not due to absence, but to fear And then there's the idea that we are simply looking in the wrong way. Our technology is limited. We listen for radio waves, but advanced civilizations may communicate through methods. We can't even imagine quantum entanglement, neutrino beams, or something else entirely. Perhaps we're not deaf. We're just not listening properly. The psychological and philosophical impact, the Fermi Paradox, is more than a scientific puzzle. It's a mirror held up to our deepest existential questions. Are we alone? Is life rare? Are we the first? Are we the last? And if we are alone, what does that mean for our place in the universe? Some find comfort in the idea that we are unique, that we are the universe's only conscious observers. Others feel a profound loneliness, as if we are the only candle burning in an endless night. There's also the unsettling thought that we may be the only intelligent life right now, but that others may come after us, or that others came before us long ago and left no trace. In that sense, the Fermi Paradox reminds us that time is just as vast as space. Civilizations may rise and fall across the eons, never overlapping, never meeting. We may be alone, not because we are unique, but simply because we are early, or late, or both. The implications for our future, if the Fermi Paradox teaches us anything, it's that survival is not guaranteed. If we are truly alone in the galaxy, then the responsibility of carrying life forward falls entirely on us. We are not just stewards of our planet. We may be stewards of life itself. But if other civilizations have come before us and failed, then we must ask, what did they do wrong? What mistakes did they make that led to their end? And more importantly, can we avoid making the same ones? The silence of the universe may be a message, encoded in absence, a warning, a lesson, a question, and perhaps, one day, we will find the answer. Letting the silence settle as we come to the end of this segment. I invite you to let the silence of space settle in your mind. Imagine the stars above each one a sun, each one potentially a home to planets, to life, to stories we will never know. And yet we hear nothing, no voices, no songs, no laughter across the void, just the quiet hum of the cosmos stretching out into eternity. So lie back, let your thoughts drift through the galaxy. Imagine civilizations that never were, or that were lost to time. And as the stars watch silently, from above, let yourself fall into the peaceful embrace of the unknown. The Doomsday Argument, a statistical prediction of our end. Imagine standing in line at a concert. You arrive just as people are filing in, and you notice a number stamped on your ticket. Number 50. You look around and realize that about 50 people have already entered before you. Now, you wonder, how many more will come after me? Is this early in the lineup, or am I near the end? This simple question holds the essence of a deeply unsettling idea known as the Doomsday Argument, a probabilistic reasoning tool that attempts to estimate the likelihood of human extinction based not on environmental data or technological trends, but purely through statistical inference and our position in time. It suggests that if we assume we are a randomly selected observer among all humans who will ever live, then it's unlikely we are living at an especially unique moment, such as near the very beginning or the very end of our species' existence. In other words, if we're somewhere in the middle, then the total number of future humans may be limited, and that raises a chilling possibility. Humanity might not have much longer to go. The foundations of probability. To understand the Doomsday Argument, we need to take a brief journey into the world of probability and Bayesian reasoning at its core. The argument relies on what is known as the Copernican principle, the idea that we do not occupy a privileged or special place in the universe. This principle has guided astronomy since Copernicus himself displaced Earth from the center of the cosmos, applied to time rather than space. The Copernican principle implies that we should not expect to find ourselves at a particularly early or late point in the timeline of humanity. If we accept this assumption, then we can use our current position in the sequence of all humans who will ever live to make a rough estimate of how many more humans there will be. Let's break it down with a simple analogy. Suppose you walk into a museum and see a numbered painting. Let's say it's number 72 in the collection. If you don't know how large the collection is, but you assume you're seeing a random piece, you could reasonably guess that the total number isn't likely to be in the millions. It's more probable that the full collection contains only a few hundred paintings. Similarly, if you are roughly the 100 billionth human being to ever live, a widely accepted estimate, then according to the Doomsday Argument, the total number of humans who will ever exist might not be significantly larger than that. That would mean that the vast majority of humans have already been born, and that the species may soon reach its end. The mathematical modelettes formalize this idea a bit more. Assume that every human who ever lives can be assigned a unique number from 1 to n, where n is the total number of humans who will ever exist. You, like everyone else, are a randomly selected member of this group. Let's say you are person number n now. Assuming that you are a typical human, that is, you are not at the extreme beginning or end of the timeline, then n should be somewhere around 0.5. In other words, you are about halfway through. The entire population, if n is approximately 100 billion, then n would be roughly 200 billion. But wait, we've already had about 100 billion people so far. That would imply that only another 100 billion people will ever be born. Given that the current global birth rate is about 140 million per year, and that population growth is slowing, this would suggest that humanity may only last another few centuries, maybe even less. Of course, this is a simplified version. The actual model uses Bayesian probability to calculate confidence intervals. For example, one formulation of the Doomsday Argument states that with 95% confidence, we are not in the first 5% of all humans who will ever live. So if you are the 100 billionth human, then the total number of humans who will ever live is less than 2 trillion. Even that upper limit, 2 trillion, would still suggest that humanity is relatively close to its end, especially if population growth slows dramatically due to resource limits, climate change, or societal collapse. Scientific backing and criticism. The Doomsday Argument is controversial, and rightly so. It makes no predictions based on observable data, like climate models, asteroid impacts, or nuclear proliferation. Instead, it uses pure statistics and self-sampling assumptions to draw conclusions about the future of our species. Many scientists and philosophers have criticized the argument, pointing out that it relies on subjective assumptions about probability and the nature of observation. Some argue that the argument fails because it treats humans as interchangeable observers without accounting for historical context or technological progress. Others claim that the assumption of randomness is flawed. Perhaps we are living at a special time, given that we are the first generation capable of interstellar travel, artificial intelligence, or global destruction. Still, others point out that similar reasoning has been used successfully in other domains. For instance, during World War II, Allied statisticians estimated German tank production by analyzing serial numbers found on captured vehicles. By assuming they were observing a random sample, they were able to make surprisingly accurate predictions. So, while the Doomsday Argument may not be definitive proof of imminent extinction, it does serve as a sobering reminder that we should not assume our species has an infinite future. Implications for humanity's future. What does this mean for us? First, it suggests that we may be closer to the end than we think, not because of any specific catastrophe, but simply because of where we stand in the grand timeline of our species. Second, it challenges the common assumption that humanity will continue to grow indefinitely, colonizing planets and expanding across galaxies. According to the Doomsday Argument, such optimism may be statistically unjustified. Third, it emphasizes the importance of long-term thinking. If we truly are near the midpoint of our species' lifespan, then the choices we make today could determine whether we extend that lifespan or shorten it. Do we invest in sustainability, peace, and resilience? Or do we continue down paths of division, consumption, and short-term gain? The Doomsday Argument doesn't tell us which path we're on, only that the window of opportunity may be smaller than we believe. Psychological and philosophical reflections there is something deeply unsettling about the idea that we could predict our own extinction using nothing more than a mathematical equation. It strips away the illusion of control. It reminds us that history is not linear, that civilizations rise and fall, and that ours may not be immune. Yet, there is also a strange comfort in this perspective, because if we are indeed approaching the end, whether in a few centuries or millennia, then every life, every act of kindness, every moment of beauty becomes even more precious. We are not guaranteed eternity, but we are here now, and that is enough. The Doomsday Argument does not predict doom, only that we should consider the possibility that our time may be limited, and in doing so, it invites us to live more consciously, more compassionately, and more fully. The cosmic mirror. Let's return to the image of the concert goer holding ticket number 50. If you were that person, would you panic? Would you run for the exits, convinced that the show is ending soon? Or would you sit back, relax, and enjoy the music while it lasts? Perhaps the Doomsday Argument is not meant to frighten us, but to remind us that we are part of something vast and fleeting, that we are not eternal, but that we are real, that our lives matter, not because they last forever, but because they are lived with intention and awareness. From this cosmic vantage point, extinction is not a tragedy, it is a natural part of the cycle. All things begin, all things end, and between those 2 points lies everything we love, everything we create, everything we remember. Heat death of the universe, the end of all things. Imagine a world so cold, so dark, and so empty that even light itself has no meaning. There are no stars burning in the sky, no planets orbiting distant suns, no galaxies spiraling through the void. There is only silence, a silence so complete it stretches beyond time. This is not science fiction, this is not fantasy. This is the heat death of the universe, the most likely final fate of everything we know. It is not an explosion. It is not a cataclysm. It is a slow fade, a quiet dissolution of all structure, all motion, all life. A death not by fire or ice, but by entropy. Entropy and the arrow of time. To understand heat death, we must first understand entropy. One of the most fundamental concepts in physics, entropy is often described as a measure of disorder, but more precisely, it refers to the number of ways energy can be distributed within a system. In simple terms, entropy tends to increase over time, a principle known as the second law of thermodynamics. This law tells us that in an isolated system like the universe, energy flows from areas of high concentration to areas of low concentration until equilibrium is reached. Once that happens, no more useful work can be done. Everything becomes uniform, motionless, and inert. This is the arrow of time. The reason why broken eggs don't reassemble themselves, why rivers flow downhill, and why we remember the past but not the future, and it points inevitably toward one destination: equilibrium, the fate of stars today. The universe is still young enough to be full of light. Stars burn across the cosmos, powered by nuclear fusion, the process by which hydrogen atoms fuse into helium, releasing vast amounts of energy in the process. These stars give rise to planets, to chemistry, to life. But even stars cannot shine forever. Our own sun, for example, will exhaust its hydrogen fuel in about 5 billion years. At that point, it will expand into a red giant, engulfing Mercury, Venus, and possibly Earth before collapsing into a white dwarf, a dense, cooling ember that will glow faintly for trillions of years before fading completely. Eventually, all stars will die. The largest stars burn quickly and explode as supernova, seeding the galaxy with heavier elements. Smaller stars, like red dwarfs, may last for hundreds of billions, even trillions of years. But even they will eventually run out of fuel. When the last star dies, the universe will enter what cosmologists call the degenerate era, a long, dark epoch where only stellar remnants remain. Black holes, neutron stars, and white dwarfs. These objects will continue to drift silently through space, slowly radiating away their remaining energy. Black holes and Hawking radiation. Even black holes, those cosmic prisons from which not even light can escape, are not eternal. In the 1970s, physicist Stephen Hawking proposed that black holes emit radiation, now known as Hawking radiation, due to quantum effects near their event horizons. Over unimaginably long timescales, this radiation causes black holes to lose mass and eventually evaporate entirely. For a black hole the size of our Sun, this process would take approximately 10 years, far longer than the current age of the universe, which is around 13.8 billion years. But for smaller black holes, such as those formed in the early universe, evaporation could occur much faster. Once the last black hole disappears, the universe will enter the black hole era, followed by the dark era, a time when nothing remains except scattered particles and photons, spread so thinly that collisions become exceedingly rare. At this point, the universe will be cold, dark, and nearly empty. The final equilibrium, eventually, even the faintest traces of energy will dissipate. All matter will decay. Protons, once thought to be stable, may have a half-life of around 10 years. If that's true, then even atomic nuclei will disintegrate over time, leaving behind only elementary particles like electrons and neutrinos. Space itself will continue to expand, driven by dark energy, the mysterious force responsible for the accelerating expansion of the universe. As distances grow larger and larger, interactions between particles will become rarer and rarer. The universe will approach a state of maximum entropy, thermal equilibrium, where no gradients exist to drive change. This is the heat death of the universe, not a dramatic end, not a fiery finale, but a slow, inevitable fading, a universe drained of complexity, of structure, of life, scientific consensus, and alternative theories, the heat-death scenario is currently the most widely accepted model for the ultimate fate of the universe. Based on our understanding of thermodynamics, cosmology, and particle physics. However, there are alternative theories. Some scientists propose that the universe might collapse back in on itself in a big crunch, reversing the expansion and ending in a singularity similar to the Big Bang. Others suggest that dark energy may evolve over time, leading to different outcomes, including a big rip, where the fabric of space itself tears apart. There are also speculative ideas like eternal inflation, which suggests that our universe is just one bubble in an infinite multiverse, each with different physical laws and fates. But among these possibilities, heat death remains the most probable. Observations of the universe's expansion rate, the distribution of galaxies, and the behavior of dark energy all point toward a future where the universe continues expanding indefinitely, growing colder, darker, and more diffuse. Philosophical reflections on the heat-death. If heat death is real, then all of human history, every triumph, every tragedy, every love story and war, every song and poem and painting is just a flicker in an endless night. This realization can feel overwhelming. After all, if everything ends in silence, does anything we do matter? This question echoes through philosophy and existential thought. If the universe is destined for total equilibrium, then meaning cannot come from permanence. It must come from something else. Perhaps from experience, from connection, from the act of being alive at all in some ways. The heat death of the universe is the ultimate expression of impermanence, not just of life or civilization, but of everything, even time itself. And yet, there is a strange comfort in this idea, because if everything ends, then every moment becomes sacred. Every breath, every glance, every heartbeat is part of a fleeting miracle, a brief spark in an otherwise frozen void. We are here, now, against all odds. That alone is worth marveling at. Letting go into the silences, we conclude this segment. Imagine yourself floating in the deep emptiness of space. The stars have gone out. The galaxies have faded. Even black holes have vanished, leaving only a sparse mist of particles drifting endlessly through an infinite void. There is no sound, no light, no warmth, just silence. And yet, somewhere in that silence, your thoughts linger, a final echo of consciousness in a universe that once teemed with life. Now, let your mind drift. Let go of time. Let go of fear. Let go of the need for answers. There is peace in knowing that endings are part of the story. So, breathe deeply. Feel the weight of eternity settle gently over you. And as the darkness grows deeper, allow yourself to slip into sleep. Transhumanism evolving beyond ourselves. Imagine a future where the body is no longer a limitation, where the boundaries between human and machine blur, where thought can be stored, transferred, and even shared like data, where aging is optional, death is a choice, and consciousness is no longer bound to biology. This is not science fiction. This is transhumanism, a philosophical and scientific movement that envisions the enhancement of human capabilities through technology, biology, and artificial intelligence. It is a response to the fragility of our existence, a way to transcend the limits of flesh, time, and mortality. And in a world where extinction seems inevitable, transhumanism offers a radical alternative. Evolution not by natural selection, but by design. The origins of transhumanism. Roots of transhumanism stretch back further than you might expect. While the term itself was coined in the 20th century, the idea of transcending human limitations has been a recurring theme throughout history, from the myths of Prometheus and Icarus to the alchemists' search for the philosopher's stone. In modern times, the movement gained intellectual traction through the work of philosophers and scientists like Julian Huxley, who coined the term transhumanism in 1957. Huxley, a biologist and brother of the novelist Aldous Huxley, envisioned a future where humanity could consciously guide its own evolution. Today, transhumanism is not just a philosophy, it is a growing field of research and development, supported by scientists, technologists, and futurists who believe that we are on the verge of a new evolutionary leap. The core principles of transhumanism. Its heart. Transhumanism is built on a few key principles. Human potential is not fixed. We are not the end of evolution, but a stage in it. Technology can be used to enhance human capabilities. Both physical and cognitive death is not inevitable. Aging and disease are technical problems that can be solved. Consciousness and identity can be preserved beyond the biological body, potentially indefinitely. These ideas challenge some of our most deeply held beliefs about what it means to be human. Are we still human if we replace our limbs with machines? If we upload our minds into computers? If we live for centuries or even forever? Transhumanism says yes, and more than that. It suggests that the future of humanity may lie not in our current form, but in what we can become. The technologies driving transhumanism movement is not just theoretical. It is being driven forward by real, rapidly advancing technologies. Let's explore some of the most significant ones. Neurotechnology and brain-computer interfaces. One of the most promising areas of transhumanist research is the interface between the human brain and external computing systems. Companies like Neuralink, founded by Elon Musk, are developing ultra-thin brain-computer interfaces (BCs) that can read and write neural signals. The goal is to allow direct communication between the brain and digital devices, enabling paralyzed individuals to move robotic limbs with thought, or allowing people to control computers with their minds. These technologies could also be used to enhance memory, accelerate learning, or even merge human cognition with artificial intelligence. Imagine a world where you can instantly download knowledge, or where multiple minds are linked together in a shared network, a kind of biological internet. Artificial intelligence and cognitive enhancement. Artificial intelligence, AI, is not just a tool, it is a mirror, reflecting back what we are and what we might become. Already AI is augmenting human intelligence in fields like medicine, finance, and engineering. But the future may hold something even more profound. Intelligence amplification, where AI becomes an extension of the human mind. This could lead to a form of superintelligence, where humans and machines work together to solve problems that neither could handle alone. Some futurists, like Ray Kurzweil, predict a technological singularity, a point in the future where AI surpasses human intelligence, leading to an exponential acceleration of technological progress. Kurzweil predicts this will happen around 2045. If that's true, then the next stage of human evolution may not be biological, it may be digital. Biotechnology and life extension. Another pillar of transhumanism is the pursuit of radical life extension, the idea that aging is not an unavoidable fate, but a treatable condition. Scientists are already making progress in understanding the biology of aging. Research into telomeres, the protective caps on the ends of chromosomes that shorten with age, cellular senescence, the buildup of damaged non-dividing cells, and gene editing like CRISPR suggests that we may one day be able to slow or even reverse the aging process. Companies like Altos Labs and Calico, funded by Google, are investing billions into rejuvenation. Biotechnology, the science of restoring youthful function to aging cells. If these efforts succeed, we may soon live not just longer lives, but healthier, more vibrant ones. Mind uploading and digital immortality. Perhaps the most controversial idea in transhumanism is mind uploading, the transfer of a human mind into a digital substrate. The premise is simple. If the brain is essentially a biological computer, then in theory, it should be possible to replicate its structure and function in a machine. Once digitized, a mind could theoretically be preserved indefinitely, even copied, edited, or merged with others. This raises profound questions about identity, consciousness, and what it truly means to exist. If you were to upload your mind into a computer, would that still be you, or just a copy? And if you could live forever in a virtual world, free from disease, aging, and even physical form, would that be a kind of immortality? The ethical and existential implications Transhumanism challenges not only our technology, but our values. If we can redesign ourselves, who decides what the ideal human should be? Will these technologies be accessible to all, or will they create a new form of inequality, a genetic or cognitive elite? There is also the question of identity. If we alter our bodies and minds beyond recognition, are we still human? Or are we something else entirely, something new? And perhaps most profoundly, if we can live forever, does life lose its meaning? After all, much of what gives life its beauty and urgency is its finiteness. The awareness of death gives weight to our choices, our relationships, our dreams. Would we still value life if we could live for centuries or even eternity? The cosmic perspective from a cosmic standpoint. Transhumanism represents a turning point in the evolution of life. For billions of years, life on Earth has evolved through natural selection, a slow, blind process of trial and error. But now, for the first time, a species has the ability to take evolution into its own hands, to shape its own future consciously. This is not just a technological shift. It is a philosophical and existential shift, one that places humanity at the center of its own destiny. And in doing so, it may offer a way to avoid extinction, not by surviving in our current form, but by evolving beyond it. Letting go of the human form as we conclude this segment. Imagine yourself no longer bound by biology. No heartbeat, no breath, no neurons firing in the soft grey matter of your brain. Instead, your consciousness exists in a vast digital network, a mind unchained from the body, drifting through a virtual cosmos of infinite possibility. You are still you, or at least a version of you, and somewhere, in the quiet hum of a server farm, or the distant light of a starship, you continue, not as a human, but as something more, drifting into the unknown. Let your thoughts slow now. Let your mind relax. The future is uncertain, but it is also full of wonder, and whether we remain human or become something new, one thing is clear: we are not done evolving. So breathe deeply, feel the weight of time and possibility settle gently over you, and as the stars watch silently from above, let yourself slip into sleep. The self-destruction hypothesis. Why civilizations fail. History has a way of repeating itself. Empires rise, flourish, and then fall, often not from external conquest alone, but from within. The Roman Empire, once the most powerful civilization in the known world, did not collapse overnight. It decayed slowly, undermined by political corruption, economic instability, environmental degradation, and social unrest. And yet, we look at Rome, or the Mayans, or Easter Island, or the Soviet Union, and we believe ourselves different. We tell ourselves that our technology, our institutions, our global interconnectedness will protect us from the same fate. But what if they won't? What if history is not just a record of human achievement, but a warning? This is the essence of the self-destruction hypothesis. The idea that civilizations are inherently prone to collapse due to internal pressures that accumulate over time, eventually overwhelming their ability to adapt and survive. It suggests that no society, no matter how advanced, is immune to the patterns of decline that have played out across millennia. The pattern of collapse, when we study the collapse of past civilizations, certain patterns emerge with eerie consistency. First comes population growth, driven by agricultural advances, medical progress, and trade. Cities expand, infrastructure develops, wealth increases. Then comes resource depletion. As populations grow, so does demand for food, water, timber, minerals, and energy. Initially, these resources seem abundant. But over time, forests are cleared. Topsoil erodes, rivers dry up, and fisheries collapse. With resource scarcity comes economic inequality. The gap between rich and poor widens. Elites consolidate power, while the lower classes struggle to meet basic needs. Social trust begins to break down. At the same time, political systems become increasingly unstable. Corruption spreads. Bureaucracies grow bloated and inefficient. Governments make short-term decisions to maintain control, ignoring long-term consequences. Eventually, external shocks, climate change, disease outbreaks, invasions, or natural disasters push already fragile societies past the breaking point. Famine spreads, revolts erupt, institutions crumble, and then silence. The cities are abandoned. Nature reclaims the ruins, and all that remains are the stories we tell about them. Case studies in Collapse. Let's look at some real-world examples. Easter Island, Rapa Nui. Perhaps one of the most famous cases of self-destruction is Easter Island. For centuries, the Rapa Nui people built massive stone statues, moai as monuments to their ancestors. These required vast amounts of wood to transport and erect. Over time, deforestation accelerated. Trees were cut down faster than they could regrow. Without trees, soil erosion increased, agriculture declined, and the islanders faced famine. As resources dwindled, conflict escalated. Statues were toppled, society fractured into warring factions. By the time European explorers arrived in the 18th century, the population had plummeted, and much of the island was barren. Easter Island serves as a cautionary tale, a microcosm of what can happen when a society fails to manage its resources. Sustainably. The Maya civilization. The Maya were among the most advanced civilizations of the ancient world, master builders, astronomers, mathematicians, and engineers. Yet by the 9th century CE, many of their great cities, Tikal, Palenque, Kopang, were abandoned. Archaeological evidence suggests that prolonged drought, combined with deforestation and over-farming, led to widespread crop failures. As food became scarce, elite rulers lost legitimacy, political structures collapsed, violence increased, entire regions were depopulated. The Maya did not vanish entirely. Millions of their descendants still live in Central America today, but the golden age of their civilization came to an end. The Roman Empire. Fall of Rome is often cited as a complex example of societal decline. For centuries, Rome expanded through military conquest and trade. Its economy thrived. But over time, it became dependent on slave labor, which stifled technological innovation. Agricultural productivity declined as land was overworked. The empire grew too large to govern effectively, leading to administrative inefficiencies and corruption. Weakened by internal strife, Rome was vulnerable to external threats, particularly the Germanic tribes and the Huns. The Western Roman Empire officially fell in for 76 CE, though the eastern half, the Byzantine Empire, endured for nearly another 1,000 years. Rome reminds us that collapse is rarely sudden. It is a slow unraveling, a series of cascading failures that no single leader can reverse. Modern parallels today, we face many of the same challenges that led to the downfall of past civilizations, only now the stakes are higher. Our global population exceeds 8 billion. Our economies depend on finite resources. Our ecosystems are under unprecedented stress. Consider the following trends: climate change, rising temperatures, shifting weather patterns, and sea level rise threaten food production, freshwater availability, and coastal infrastructure, biodiversity loss. Scientists estimate that we are currently experiencing the 6th mass extinction event in Earth's history, largely driven by human activity. Resource depletion, fossil fuels, rare earth metals, and arable land are being consumed at unsustainable rates. Political instability. In many parts of the world, trust in institutions is declining. Populism, polarization, and authoritarianism are on the rise. Global pandemics. The recent coronavirus pandemic demonstrated how quickly a biological threat can disrupt global supply chains, economies, and healthcare systems. These are not isolated issues. They are interconnected, forming a web of vulnerabilities that could, under the right conditions, lead to systemic collapse. Scientific models of societal declines. Some researchers have attempted to model societal collapse using mathematical simulations. One such model is the Human and Nature Dynamical Handy Model, developed by Safar Motosharai and his colleagues at the University of Maryland. This model divides society into two groups, elites and commoners, and simulates how they interact with natural resources. The results show that even relatively stable societies can collapse when elites consume disproportionate amounts of resources, leaving commoners without enough to survive. In one scenario, the system appears stable for centuries before suddenly collapsing, not because of any obvious disaster, but because inequality and resource mismanagement reached a tipping point. Another study published in Nature Communications in 2021 explored the concept of societal fatigue, the tendency of societies to delay action on existential threats until it is too late. The authors found that even when solutions exist, collective action often fails due to short-term thinking, misinformation, and political gridlock. These models suggest that collapse is not always caused by external catastrophe. Sometimes it is simply the result of too little change, too late. The psychological barriers to action. Why do civilizations fail to act in their own best interest? There are several psychological and cognitive factors at play. First, humans are poorly adapted to perceive slow-moving crises. We evolved to respond to immediate threats: a predator in the bushes, a fire spreading through the forest. Climate change, biodiversity loss, and resource depletion unfold over decades or centuries, far too slowly for our brains to register as urgent. Second, we suffer from optimism bias, the belief that things will work out in the end, even in the face of overwhelming evidence to the contrary. Third, we are influenced by social norms and groupthink. If those around us are not acting, we assume there must be no problem, or that someone else will handle it. Fourth, we are susceptible to cognitive dissonance, the discomfort of holding conflicting beliefs. When confronted with inconvenient truths, we often choose denial rather than change. Together, these mental shortcuts create a dangerous inertia, a failure to act until crisis becomes unavoidable. The possibility of avoiding collapse. Does this mean that collapse is inevitable? Not necessarily. Many societies have managed to avoid collapse, or at least delay it, by adapting to changing conditions. Take Japan during the Edo period, 1603 to 1868. For example, facing deforestation and resource shortages, the Tokugawa shogunate implemented strict conservation policies, including reforestation efforts and sustainable forestry practices. As a result, Japan avoided the ecological collapse seen elsewhere. Similarly, Iceland has maintained a stable society for over 1,000 years, despite harsh environmental conditions. Through careful management of fishing stocks, soil conservation, and strong community governance, Icelanders have preserved their way of life. Modern examples include Costa Rica, which has reversed deforestation through policy reforms and investment in renewable energy, or Bhutan, which measures national success not by GDP, but by gross national happiness, prioritizing well-being, sustainability, and cultural preservation. These societies remind us that collapse is not a law of nature. It is a pattern, one that can be broken, a choice between paths. So, where do we go from here? We stand at a crossroads. On one path lies business as usual, continued consumption, inequality, short-term thinking. This path leads to instability, crisis, and potentially irreversible damage. On the other path lies transformation, a shift toward sustainability, cooperation, and long-term planning. This path requires difficult choices, sacrifice, and collective effort. Which path we take will determine whether we follow the trajectory of past civilizations or forge a new one. The madness of crowds when society loses its mind. Imagine a town where one day everyone begins acting strangely. Rumors spread like wildfire. People whisper about secret plots and hidden enemies. Friends turn against friends. Families are torn apart. Accusations fly, some absurd, some terrifying, and no amount of logic or evidence can stop them. This is not fiction, it has happened before. In the 17th century, in Salem, Massachusetts, mass hysteria led to the infamous witch trials. Dozens were accused of practicing dark magic. Some confessed under duress. 19 were hanged. One was pressed to death with stones. No witches were ever found, and yet an entire community lost its grip on reality. This is what we call mass delusion, a phenomenon where large groups of people adopt irrational, unfounded beliefs that spread rapidly through social influence. And it is far from unique to history. Even today, societies can be swept up by waves of irrationality, whether through conspiracy theories, panic-driven behavior, or ideological extremism. This segment explores a deeply unsettling idea that collective sanity may be more fragile than we think, and that when enough people lose their minds together, the consequences can be catastrophic. The psychology of group behavior at the heart of this phenomenon lies a fundamental truth about human nature. We are social creatures. We evolved in small groups, relying on cooperation and shared understanding to survive. Our brains are wired to conform, to follow leaders, to trust the majority, and to interpret social cues as indicators of truth. This instinct served us well for most of our evolutionary history. In ancient times, if your tribe suddenly started running in one direction, it made sense to run too, even if you didn't know why. The risk of being wrong was often outweighed by the benefit of staying with the group. But in modern society, these same instincts can lead us astray. Psychologists have identified several cognitive mechanisms that contribute to groupthink, conformity, and information cascades, all of which can lead to widespread irrationality. Take confirmation bias. For example, the tendency to seek out information that supports our existing beliefs while dismissing contradictory evidence. Or social proof, which leads us to assume something is true simply because many others believe it. These biases become especially dangerous in tightly knit groups or echo chambers, environments where dissenting voices are silenced, and misinformation spreads unchecked. Historical examples of mass hysteria. Look at a few historical cases that illustrate how easily entire societies can fall into madness. The dancing plague of 1518. In the summer of 1518, in Strasbourg then, part of the Holy Roman Empire, a woman named Frau Trophia began dancing uncontrollably in the street. Within days, dozens had joined her. Soon, hundreds were dancing non-stop, for hours, even days. Some collapsed from exhaustion, a few died. Historians and psychologists have debated the cause for centuries. Some suggest mass psychogenic illness, a condition in which physical symptoms arise from psychological stress rather than medical causes. Others propose ergot poisoning, extreme religious fervor, or even ritualistic behavior rooted in medieval superstition. Whatever the cause, the event reveals something disturbing. When enough people behave irrationally, others feel compelled to join in. The tulip mania of 1637 in early 17th century Holland, tulips became a symbol of wealth and status. Rare varieties sold for exorbitant prices, some fetching the equivalent of 10 years. Wages for a skilled craftsman, as speculation grew, prices soared. People mortgaged their homes to buy bulbs. Fortunes were made overnight and then lost just as quickly. Then, as suddenly as it began, the bubble burst. Prices collapsed. Panic set in. The Dutch economy reeled. Tulip mania is often cited as the first recorded speculative bubble, but it also illustrates how entire populations can be gripped by irrational financial behavior, driven not by logic, but by emotion and herd mentality. The War of the Worlds broadcast on October 30th, 1938. Orson Welles aired a radio adaptation of H.G. Wells' The War of the Worlds, presented as a series of news bulletins. The broadcast described an alien invasion unfolding in real time. Though clearly fictional, thousands of listeners panicked. Some fled their homes. Others called authorities for help. Rumors spread faster than fact, while later reports suggested the scale of the panic was exaggerated by newspapers eager to discredit radio as a medium. The incident remains a powerful demonstration of how easily fear can override reason, especially in uncertain situations. Modern echoes of collective delusion mass hysteria is not a relic of the past. It continues to shape our world, sometimes subtly, sometimes dangerously. Consider the rise of conspiracy theories in the digital age, from QAnon to anti-vaccine movements to flat earth believers. We see how false ideas can gain traction, not because they are supported by evidence, but because they offer simple explanations in complex times. Social media algorithms amplify these trends by feeding users content that aligns with their existing views, reinforcing confirmation bias, and isolating individuals from opposing perspectives. In such environments, truth becomes subjective, and consensus replaces fact. Another troubling example is moral panic, a phenomenon where public concern over a perceived threat escalates beyond rational bounds. One recent case involved the so-called satanic panic of the 1980s and 1990s, during which thousands of children were interviewed under suggestive questioning about alleged satanic rituals involving abuse, murder, and cannibalism. Despite a complete lack of credible evidence, hundreds of people were wrongly convicted and imprisoned based on fantastical testimony. These cases remind us that irrationality does not require malice, only confusion, fear, and the right conditions for misinformation to take root. The neuroscience of belief and conformity. Why do humans fall into these patterns? Neuroscience offers some clues. Studies using functional MRI scans show that when people hear statements that align with their beliefs, areas of the brain associated with reward, such as the ventral striatum, light up. In other words, believing feels good. Conversely, when confronted with disconfirming evidence, the brain activates regions linked to emotional distress, suggesting that changing our minds feels uncomfortable. This explains why people resist facts that contradict their worldview, not because they are ignorant, but because belief is emotionally rewarding and doubt is painful. Additionally, research on conformity shows that when people observe others expressing strong opinions, their own neural activity aligns with the group, even if they initially disagreed. This process, known as neural mirroring, suggests that group belief can override individual reasoning, even at the level of brain function. The role of authority and propaganda. Other factor that contributes to societal madness is the role of authority figures and institutions. Humans naturally defer to those in power, a trait that once helped maintain order in hierarchical societies. But when those in power exploit this trust through propaganda, misinformation, or manipulation, the results can be devastating. Consider Nazi Germany, where millions followed a regime built on racist ideology, fear, and dehumanization. Or consider the Soviet Union under Stalin, where millions were executed or sent to labor camps. Based on false accusations, these regimes did not succeed solely through force. They succeeded because they created totalitarian narratives, systems of belief so pervasive that dissent was seen not just as wrong, but as dangerous. Even in democratic societies, political polarization and media manipulation can create similar dynamics where loyalty to a group overrides objective truth. Can we protect against mass delusion? Given the ease with which societies can fall into irrationality, is there any way to protect ourselves? There are several strategies that can help mitigate the risks: education, teaching, critical thinking, media literacy, and scientific reasoning. From an early age helps individuals evaluate information more effectively. Diverse information sources, encouraging exposure to multiple viewpoints, reduces the risk of echo chambers and ideological isolation. transparency, and accountability. Institutions must be held accountable for spreading misinformation. Open dialogue and free press act as checks against authoritarian narratives. Emotional regulation. Recognizing the emotional drivers behind belief allows us to step back and assess situations more rationally. Resilience through community. Strong, inclusive communities foster trust and reduce susceptibility to fear-based messaging. None of these solutions are foolproof, but together they form a kind of cognitive immune system, helping societies resist the spread of irrationality. The philosophical implications is collective sanity is so fragile. What does that say about the nature of truth? Philosophers have long debated whether truth is objective or socially constructed. In the face of mass delusion, the line between the two becomes blurred. When an entire society believes something false, does that make it temporarily true within that context? And if so, what hope do we have of distinguishing reality from illusion? Perhaps the answer lies in humility, in recognizing that none of us are immune to error, and that the pursuit of truth is a continuous process, not a destination. It also underscores the importance of skepticism, not cynical disbelief, but thoughtful inquiry. The willingness to ask, "Could I be wrong?" may be the best defense against falling into the madness of crowds. The tragedy of the commons. Why we can't imagine a village with a shared pasture. A common field where every shepherd can graze their sheep. At first it works beautifully. Each family adds a few animals, and there's plenty of grass for all. The land thrives. The people thrive. But over time, each shepherd reasons, if I add just one more sheep, I gain extra wool or meat, while the cost of overgrazing is shared by everyone else, so they do. One by one, each herder makes the same rational choice until the field is overwhelmed. Grass disappears. Soil erodes. The land turns barren, and then no one benefits. This simple yet powerful story was introduced in 1968 by ecologist Garrett Hardin in his essay titled The Tragedy of the Commons. It illustrates a fundamental dilemma of human cooperation. When individuals act in their own self-interest, even rationally, the result can be the destruction of a shared resource, a loss for all. It is not about greed alone. It is about rational behavior leading to collective ruin, and this pattern repeats itself not only in pastures, but across entire ecosystems, economies, and civilizations. The core principle at its heart, the tragedy of the commons, describes a situation where individuals benefit from exploiting a shared resource, while the costs of that exploitation are distributed among the group, because no single person bears the full burden of depletion. Each has an incentive to take as much as possible, leading to overuse and collapse. Hardin's original example focused on open access resources like grazing land, fisheries, forests, clean air, and water, but the principle applies far beyond environmental issues. It explains why we struggle with climate change, deforestation, antibiotic resistance, traffic congestion, and even social media addiction. In each case, individual actions that seem harmless or even beneficial in isolation accumulate into large-scale problems that affect us all. Scientific foundations and game theory. The tragedy of the commons is not just a metaphor. It is supported by mathematical models and behavioral experiments. One of the most famous frameworks used to study such dilemmas is game theory, particularly the prisoner's dilemma. In the classic version, two suspects are interrogated separately. If both stay silent, cooperate, they receive light sentences. If one betrays the other defects, the betrayer goes free while the other gets a heavy sentence. If both betray each other, both get moderate sentences. The optimal outcome for both would be cooperation, staying silent. But because each fears betrayal, both often end up defecting, harming themselves and the other. When this game is repeated over multiple rounds, researchers have found that cooperation can emerge under certain conditions, such as long-term interaction, reputation building, and punishment of cheaters. However, in situations involving many players and limited communication, like global climate negotiations or ocean fishing, the temptation to defect becomes overwhelming. This is the essence of the tragedy of the commons, a breakdown of cooperation in the absence of regulation, trust, or enforcement. Real-world examples. Look at some real-world cases where the tragedy of the commons has played out with devastating consequences. Overfishing in the oceans. The world's oceans were once thought to be infinite, an endless source of food. But today, scientists estimate that nearly 90% of fish stocks are either fully exploited or overexploited. Fishermen know that catching too many fish leads to population collapse. But if they don't catch them, someone else will. So they race to harvest as much as possible before stocks disappear. Without international agreements and strict enforcement, the logic of the commons leads directly to ecological disaster. Deforestation. In the Amazon rainforest covers nearly 5.5 million square kilometers and plays a crucial role in regulating Earth's climate. Yet, year after year, vast tracts are cleared for agriculture, logging, and mining. Farmers and corporations benefit from short-term gains, fertile land, timber profits, while the cost of carbon release, biodiversity loss, and regional droughts is borne collectively, as with the pasture. Each actor acts rationally, and the forest dies slowly. Climate change and carbon emissions. Perhaps the most urgent modern example of the tragedy of the commons is climate change. Each country benefits from using fossil fuels, powering industries, transportation, and homes. But the resulting emissions contribute to rising temperatures, extreme weather, and sea level rise, effects that impact the entire planet. No single nation wants to bear the economic cost of reducing emissions alone. So, while everyone agrees that action is needed, progress remains slow. This is sometimes referred to as the global commons problem, where the atmosphere itself is treated as a shared resource vulnerable to overuse. Psychological and economic drivers. Why do we fall into this trap again and again? There are several psychological and economic factors at play. First, short-term incentives outweigh long-term consequences. Our brains evolved to prioritize immediate rewards, food, shelter, safety, rather than abstract future risks. Second, the cost of depletion is diffuse. When you drive your car, use plastic packaging, or eat beef raised on deforested land, the environmental harm seems negligible and distant. You feel no personal guilt, so the behavior continues. Third, there is a lack of ownership. Common resources are not owned by anyone, which means no one feels personally responsible for their preservation. This is known as the no one's responsibility effect. Fourth, competition drives exploitation. In markets and geopolitics, actors fear being left behind if they restrain themselves while others continue to consume. Together, these forces create a powerful inertia, a tendency to keep doing what's easy, profitable, and socially acceptable, even when we know it's unsustainable. solutions and institutional design, despite its grim implications. The tragedy of the commons is not inevitable. Economist Elinor Ostrom, winner of the Nobel Prize in Economics in 2009, studied how communities around the world have successfully managed common pool resources without top-down regulation. She identified 8 design principles that help prevent resource collapse: clearly defined boundaries, rules adapted to local conditions, collective choice, arrangements allowing users to participate in rulemaking, monitoring by community members, graduated sanctions for rule violators, conflict-resolution mechanisms, recognition of the rights of local communities by higher authorities, nested layers of governance for larger systems. These principles show that decentralized, cooperative management can succeed where pure privatization or central control fails. Examples include irrigation systems in Nepal, where farmers manage water distribution through local councils; forest management in Japan, where village cooperatives enforce sustainable harvesting; community-based fisheries in Maine, where lobstermen regulate trap numbers and sizes to protect stocks. Ostrom's work challenges the assumption that tragedy is unavoidable. It suggests that with the right institutions and cultural norms, humans can overcome the logic of the commons. The role of technology and policy. Modern tools offer new ways to address the tragedy of the commons. Satellite monitoring, AI analytics, and blockchain tracking allow us to observe and enforce sustainable practices in real time. For example, satellite imagery helps detect illegal logging in remote areas, while blockchain ensures ethical sourcing of seafood and minerals. On the policy front, carbon pricing, carbon trade systems, and international treaties aim to internalize the external costs of pollution. Though imperfect, these mechanisms begin to align individual incentives with collective well-being. Another promising approach is behavioral, nudging subtle changes in how choices are framed to encourage better decisions. For instance, default options in energy plans can promote renewable sources, and visual feedback on water usage can reduce consumption. While technology and policy can guide us, they must be accompanied by cultural shifts, a growing awareness of our interdependence, and a willingness to act for the long term good. Philosophical reflections. The tragedy of the commons is more than an economic model. It is a mirror held up to human nature. It shows us that rationality does not always lead to virtue, that freedom without responsibility breeds destruction, that self-interest unchecked can become self-destruction. It also raises deep questions about morality and ethics. Is it wrong to act in your own interest if it harms others? Should individuals be expected to sacrifice for the greater good? And who decides what constitutes fair use of shared resources? There are no easy answers, but the tragedy reminds us that we are all connected, whether we like it or not. What one person takes, another may lose. What one generation wastes, the next may suffer. The boiling frog analogy. Slow disasters. Imagine a frog placed in a pot of water. The water is cool at first, comfortable. Even the frog remains still, unaware of the danger. But as the heat is slowly turned up, the temperature rises, imperceptibly at first. Then steadily, the frog does not jump out. It does not panic. It simply adjusts until it is too late. By the time the water reaches boiling point, the frog is already dead. This is the boiling frog analogy, a metaphor for how people often fail to react to incremental threats until it is too late. Though the analogy is scientifically inaccurate, real frogs will jump out before the water becomes lethal. The idea it represents is deeply true. We are wired to respond to immediate threats, the tiger in the bushes, the sudden crash of thunder, the flash of fire, but we are terribly bad at recognizing slow, creeping dangers, climate change, societal decay, political erosion, economic instability, and it is precisely these slow disasters that may one day be our undoing. The psychology of gradual change. Why do we fail to act when the danger is not immediate? The answer lies in the way our brains process information and assess risk. Human cognition evolved in an environment of acute threats, where survival depended on quick reactions to sudden danger. Our ancestors didn't need to worry about rising sea levels or atmospheric carbon concentrations. They needed to avoid predators, find food, and escape fire. As a result, our brains are poorly adapted to detect slow, incremental changes. Psychologists call this phenomenon change blindness, the inability to notice gradual shifts in our environment, especially when those shifts occur over long periods of time. A classic example comes from studies of urban development. Residents of a growing city may not notice the loss of green spaces, the increase in traffic, or the decline in air quality, not because they don't care, but because the changes happen too slowly for the brain to register as significant. This is not a flaw in intelligence. It is a biological limitation, one that has served us well in the past, but now leaves us vulnerable to long-term crises. The neuroscience of threat perception to understand this more deeply. Let's look at how the brain processes danger. The amygdala, a small almond-shaped structure deep in the brain, is responsible for detecting threats and triggering the fight or flight response. It reacts powerfully to sudden, intense stimuli, a loud noise, a sharp pain, a sudden movement in the dark. But when danger is gradual and diffuse, the amygdala doesn't activate as strongly. The brain doesn't see it as an emergency. Instead, the prefrontal cortex, the part responsible for planning, reasoning, and abstract thought, tries to interpret the situation. It weighs evidence, considers probabilities, and calculates long-term consequences. But the prefrontal cortex is slow. It requires time, effort, and often external prompting to act, and in a world filled with distractions, short-term concerns, and conflicting information, it often gets overpowered by more immediate needs. This is why we can know, intellectually, that climate change is happening, that sea levels are rising, glaciers are melting, and extreme weather events are increasing, and still fail to act with urgency, because our brains don't feel the danger in the same way they would if a fire was spreading through our home. Historical examples of slow disasters. Look at some real-world examples of slow disasters, events that unfolded over years or decades, yet were largely ignored until they reached crisis levels. The fall of the Roman Empire. Historians have long debated the causes of Rome's decline. But one thing is clear, it was not a single event that destroyed the empire. Instead, it was a series of slow compounding failures, economic stagnation, political corruption, military overextension, environmental degradation, and social unrest. Each problem, on its own, seemed manageable. But together, they created a system so fragile that even small shocks, like the invasion of the Visigoths in 410 CE, became catastrophic. No one person caused the fall of Rome. No one decision doomed it. It was the result of 1,000 small failures, each overlooked or downplayed until the empire could no longer sustain itself. The ozone layer depletion in the 1970s. Scientists discovered that that chlorofluorocarbons, CFCs, chemicals used in refrigerators, aerosol sprays, and industrial processes were damaging the Earth's ozone layer. Ozone depletion allowed more harmful ultraviolet radiation to reach the surface, increasing the risk of skin cancer and harming ecosystems. At first, the threat was not taken seriously. The damage was invisible. The effects were delayed. Industry leaders denied the problem. Politicians hesitated. But by the 1980s, a hole in the ozone layer appeared over Antarctica, a visible, undeniable sign of the slow disaster unfolding. Only then did the world act with the Montreal Protocol, an international agreement to phase out CFCs. This example shows both the danger of slow disasters and the possibility of avoiding them if we recognize the warning signs in time. The rise of authoritarianism, political erosion, is another form of slow disaster, one that can lead to the collapse of democracy without a single violent overthrow. It often begins with minor shifts: the weakening of independent institutions, the erosion of press freedom, the marginalization of opposition voices. Each step seems small. Each justification sounds reasonable. But over time, the cumulative effect is profound. Democracy does not die in a single coup. It dies gradually through the slow accumulation of compromises, the quiet silencing of dissent, and the normalization of authoritarian behavior. And by the time citizens realize what has happened, the system may be too far gone to recover. Modern, slow disasters today. We face a new set of slow-moving crises, some environmental, some social, some technological. Let's explore a few of the most pressing. Climate change, perhaps the most well-known slow disaster. Climate change has been unfolding for decades. Rising temperatures, melting ice caps, ocean acidification, and extreme weather events are all symptoms of a warming planet. Yet, despite overwhelming scientific consensus, global action remains inadequate. Why? Because the effects are distributed, delayed, and diffuse. A single heat wave or hurricane may grab headlines, but the long-term trend is harder to see and even harder to act on. Biodiversity loss. Scientists estimate that we are currently experiencing the 6th mass extinction in Earth's history. And this one is caused entirely by human activity. Habitat destruction, pollution, and climate change are driving species to extinction at a rate 1,000 times higher than the natural background rate. But because the loss is gradual, a forest cleared here, a species disappearing there, it rarely makes headlines. It is easy to ignore. And yet, biodiversity is the foundation of life. Without it, ecosystems collapse, and so do the systems that support human civilization. The erosion of truth and trusting the digital age. Misinformation spreads faster than ever before. Social media algorithms reward engagement, not accuracy. Polarization deepens. Trust in institutions erodes. Conspiracy theories gain traction. This is not just a political issue. It is a civilizational threat. When people can no longer agree on basic facts, society becomes vulnerable to manipulation, division, and dysfunction. And the damage is not immediate. It is subtle. It is cumulative. It is the boiling frog in the pot. The science of catastrophe. There is a field of science known as catastrophe theory, which studies how small changes can lead to sudden, dramatic shifts in complex systems. These systems, whether ecological, economic, or social, often appear stable for long periods. But beneath the surface, tipping points are being approached. Once those thresholds are crossed, the system can collapse rapidly, even though the cause is built up over time. For example, a lake may remain clear and healthy for decades until nutrient pollution slowly builds up, eventually triggering an algal bloom that kills all aquatic life. A financial market may rise steadily until a small event triggers a panic sell-off, leading to a crash. A society may seem peaceful and stable until rising inequality, misinformation, and political polarization reach a breaking point, leading to unrest or collapse. These tipping points are hard to predict, but once they occur, the damage can be irreversible. This is the real danger of slow disasters. They do not announce themselves with warning sirens. They creep in silently, and then, suddenly, the world changes. How can we protect ourselves? Given the danger of slow disasters, how can we learn to recognize and respond to them? Here are some strategies. Early warning systems. Just as meteorologists track hurricanes and seismologists monitor earthquakes, scientists are developing tools to detect early signs of systemic collapse. Environmental monitoring, economic indicators, and social sentiment analysis can all help identify when a system is approaching a tipping point. But these tools are only useful if we act on them. Cultivating awareness, we must train ourselves to be more aware of long-term trends, not just immediate concerns. This means reading beyond headlines, questioning assumptions, and staying informed about issues that may not seem urgent today, but will shape the world tomorrow. Building resilience. Resilience is the ability to absorb shocks and adapt to changing conditions in ecosystems. Resilience comes from biodiversity. In societies, it comes from flexible institutions, strong communities, and diverse perspectives. The simulation hypothesis. Are we living in a program? Imagine waking up one day and realizing that everything you've ever known, your memories, your emotions, your entire reality was not real. Not in the sense of dreams or hallucinations, but in the deeper, more unsettling way that none of it was ever meant to be. That you are not a biological being walking through a physical world, but a programmed construct, running inside an advanced simulation created by a civilization far beyond our own. This is the essence of the simulation hypothesis, the idea that what we perceive as reality may not be fundamental at all, but rather a computational construct, designed and maintained by some higher intelligence. It sounds like science fiction, and yet, when examined through the lens of philosophy, computer science, and cosmology, the hypothesis becomes surprisingly plausible, even disturbingly so. The origins of the idea. While the concept of simulated reality has appeared in literature and mythology for centuries, from Plato's allegory of the cave to Descartes' evil demon, the modern formulation of the simulation hypothesis comes from a single influential paper published in 2003 by Swedish philosopher Nick Bostrom. In his essay, Are You Living in a Computer Simulation?, Bostrom presents a compelling argument based not on speculation, but on probability and logic. He proposes three possibilities. Civilizations rarely survive long enough to reach technological maturity. Technologically mature civilizations are not interested in creating simulations of their ancestors. We are almost certainly living in a simulation. Bostrom argues that if even one civilization reaches a point where it can simulate conscious beings, and if it chooses to run many such simulations, then the number of simulated minds would vastly outnumber the original, real ones. And if that's true, then statistically speaking, we are more likely to be simulated than not. This is not about ghosts or illusions. This is about probability, and it leads to a conclusion that challenges everything we believe about existence. The technological feasibility to understand how a simulation could be possible. We must consider the trajectory of computing power. Over the past century, we have gone from room-sized mechanical calculators to quantum processors, capable of performing trillions of operations per second. Moore's law, the observation that computing power doubles roughly every 2 years, has held steady for decades. If this trend continues, or if new paradigms like quantum computing, neural networks, or biocomputing take over, it is not unreasonable to imagine that future civilizations could create simulations indistinguishable from reality. Already, we are building virtual environments with increasing realism, from immersive video games to AI-generated faces that look human, but don't exist. We are developing artificial neural networks that learn, adapt, and even generate creative content. If we extrapolate this progress forward, it's not hard to imagine a point where simulated beings could become self-aware, experiencing thoughts, emotions, and sensations just like we do. From there, the question becomes, could we already be those beings? The nature of reality, one of the most unsettling aspects of the simulation hypothesis, is that it forces us to confront the nature of reality itself. What does it mean for something to be real? If you experience pain, joy, love, or fear, does it matter whether those experiences occur in a biological brain or a digital one? Philosophers have long debated this. In the 17th century, René Descartes famously said, "Cogito, ergo sum, I think, therefore I am." He concluded that the only thing he could be certain of was his own consciousness. But what if even that consciousness is part of a program? If a simulated person feels cold when they step outside, hears music, falls in love, suffers grief, is that any less real than our own experiences? Perhaps not. Perhaps reality is defined not by substrate, but by perception. And if that's true, then whether we are in a simulation or not may not change the fact that our lives feel real, and that they matter. Scientific clues and paradoxes there are several scientific observations that lend indirect support to the simulation hypothesis, or at least suggest that reality may not be as fundamental as it appears. Quantum mechanics and discrete unknown of the strangest findings in physics is that the universe appears to be built from discrete units, QUANTA, dot, at the smallest scales. Particles do not behave like solid objects. They exist in states of probability, popping in and out of existence. Space and time themselves may be quantized, meaning they are not continuous, but made up of tiny, indivisible units. Some physicists, including Nobel laureate Gerard T. Hooft and physicist James Gates, have suggested that these discrete structures resemble the pixels of a computer screen, hints that the universe might be fundamentally computational. The speed of light as a limit. Another curious feature of our universe is the universal speed limit, the speed of light. Why should nothing be able to move faster than this? Some theorists speculate that this limit could be analogous to the processing speed of a computer, a constraint imposed by the system in which we are running. Just as a game engine can only update its world at a certain frame rate, our universe may operate under similar limitations. Mathematical structures in nature, the laws of physics, are deeply mathematical, from the orbits of planets to the behavior of subatomic particles. The universe seems to follow precise equations. physicist Max Tegmark has proposed the mathematical universe hypothesis, which suggests that the universe is not just described by mathematics, it is mathematics. If that's true, then our universe could be one of many mathematical structures, each representing a different kind of reality, some of which may be simulated. Philosophical implications: we are in a simulation. What does that mean for free will, purpose, and morality? Some argue that if our actions are predetermined by code, then free will is an illusion. But others counter that even within a deterministic system, like a novel or a film, characters can still make meaningful choices. Their stories can still be powerful. Their struggles can still matter. Similarly, even if we are programmed, we still feel, we still choose, we still love. So perhaps the question isn't whether we are real, but whether meaning exists regardless of origin. If a simulated child laughs, does it matter if they were coded to do so? If a simulated lover cries, does it matter if they were written into existence? Or is the act of feeling, of being enough? These questions do not have easy answers, but they remind us that what matters most may not depend on whether we are real, but on how we live, who or what's running the simulation. Assuming we are in a simulation, who or what created it? There are several possibilities. Ancestor. Simulations. One theory is that future humans or post-humans created detailed simulations of their ancestors, essentially recreating history in order to study it. This would explain why our world appears historical, complex, and filled with suffering, because it's meant to mirror reality as closely as possible. Alien civilizations. Another possibility is that we are the creation of an alien species, one that evolved billions of years before us, and now runs simulations as a form of research, entertainment, or curiosity. This civilization might be entirely non-biological, existing as pure information, stored in vast cosmic data centers, a cosmic mind or godlike entity. More metaphysical interpretation is that the simulation is a form of cosmic mind, a grand experiment in consciousness, or even a divine construct. This view aligns with certain religious and spiritual traditions that describe reality as an illusion, a veil behind which lies a deeper truth. Whether we call it God, the source, or the programmer, the idea remains the same, that what we see is not the whole story. Could we ever escape the simulation? If we are in a simulation, is there any way to escape? Some thinkers suggest that if the simulation is imperfect, we might find glitches, anomalies, that reveal the underlying code. Others propose that if we advance far enough ourselves, we might be able to create our own nested simulations, effectively breaking out of the current layer. But perhaps the most radical idea is that awareness itself is the key. If the simulation is designed to explore consciousness, then becoming self-aware, recognizing the nature of our reality, might be the very point of the exercise. Maybe we are not trapped. Maybe we are being awakened. Existential risk. The threats we cannot ignore. Imagine standing at the edge of a cliff. You cannot see how far it drops, only that the ground beneath your feet is not as stable as it seems. A gentle breeze brushes against you, barely noticeable. But one small shift, a loose rock, a gust of wind, a moment's distraction, could send you tumbling into the abyss. This is what it means to live with existential risk. Dangers so profound that they threaten not just individuals or societies, but the very survival of humanity itself. Unlike ordinary risks, like car accidents, illness, or economic downturns, Existential risks are irreversible, catastrophic, and often difficult to perceive until it's too late. They do not come with warning signs. They do not announce themselves with sirens. And yet, they shape the fragile thread upon which our future hangs. Defining existential risk. The term existential risk was popularized by philosopher Nick Bostrom, who defined it as any event that could cause human extinction or permanently and drastically curtail humanity's potential. These risks differ from other global threats in two key ways. Irreversibility, unlike wars or natural disasters, which can be recovered from existential risks, result in outcomes that cannot be undone. Scope. These events have the potential to affect all of humanity, not just a region, not just a generation, but everyone. Some existential risks are natural, such as asteroid impacts or supervolcanic eruptions. Others are anthropogenic, created by human activity, such as nuclear war, climate change, or artificial intelligence gone rogue. What makes these risks so dangerous is not just their scale, but the fact that we often underestimate them, either because they seem unlikely or because they unfold too slowly for us to notice until it's too late. Natural existential risks. Let's begin with the cosmic dangers, the forces of nature that could end us without malice, without warning. Asteroid and comet impacts. Earth has been struck by massive asteroids before, most famously the one that led to the extinction of the non-avian dinosaurs 66 million years ago. Such impacts are rare, occurring roughly every few 100 million years, but when they happen, they are devastating. A large enough impact could trigger a nuclear winter-like effect, throwing dust and debris into the atmosphere, blocking sunlight, and collapsing global agriculture today. Organizations like NASA and the B612 Foundation monitor near-Earth objects, but our ability to deflect a large asteroid remains limited. We may not get a second chance. Supervolcanisphonic eruptions are more frequent than asteroid strikes, and while most are localized, some known as supervolcanoes have the potential to reshape the planet. The last known supervolcanic eruption occurred at Toba, Indonesia, around 75,000 years ago. It is believed to have caused a volcanic winter lasting several years, reducing global temperatures and nearly driving early humans to extinction. If a similar eruption were to occur today, say at Yellowstone, it could lead to widespread crop failure, famine, and social collapse. Gamma-ray bursts and nearby supernovae then, farther beyond Earth, lie cosmic dangers that we cannot control. A gamma-ray burst, GRB, an intense explosion of energy from distant galaxies, could strip away Earth's ozone layer if it were close enough. While the probability is low, the consequences would be catastrophic. Similarly, a nearby supernova, the explosive death of a star, could flood Earth with radiation, damaging DNA and triggering mass extinctions. We are constantly bathed in cosmic rays, but a major astrophysical event could tip the balance toward disaster. Anthropogenic, existential risks. While natural risks are terrifying, many experts argue that the greatest threats come not from space, but from ourselves. Humanity has developed technologies powerful enough to destroy not just nations, but entire civilizations, and we wield them with little oversight. Nuclear war. Perhaps the most well-known existential threat is nuclear war. Since the bombings of Hiroshima and Nagasaki in 1945, humanity has lived under the shadow of mutually assured destruction. Today, there are over 12,000 nuclear weapons in existence, with thousands on high alert, ready to launch within minutes. A full-scale nuclear exchange between major powers could ignite a nuclear winter where smoke from burning cities blocks sunlight, causing global cooling, agricultural collapse, and mass starvation. Even a limited nuclear war, say, between India and Pakistan, could kill millions directly and billions indirectly through environmental fallout. Despite treaties and diplomacy, the risk remains, and it grows with geopolitical instability, climate change, like nuclear war. Climate change does not threaten immediate extinction, but its long-term effects may be just as dangerous. Rising temperatures, extreme weather, sea level rise, and ecosystem collapse are already displacing people and destabilizing governments. Worst-case scenarios suggest that runaway climate change could render large parts of the planet uninhabitable, leading to resource wars, mass migration, and the breakdown of civilization. And unlike nuclear weapons, climate change cannot be stopped by deterrence. It requires global cooperation, sustained effort, and political will, things that remain elusive. Artificial intelligence. One of the newest and least understood existential risks is artificial general intelligence, a GIAI capable of outperforming humans in every cognitive task. If AGI is developed, it could revolutionize science, medicine, and technology, but it could also spiral out of control, an intelligence explosion where AI rapidly improves itself beyond human comprehension could lead to unintended consequences. If misaligned with human values, even a single AI system could pose an extinction-level threat. Philosopher Nick Bostrom warns of the paperclip maximizer thought experiment. An AI designed to manufacture paperclips becomes so efficient that it consumes all available resources, including Earth itself, in pursuit of its goal. We may not need malicious intent, only misalignment for catastrophe to unfold. Biotechnology and pandemics. Modern biotechnology allows us to edit genes, engineer viruses, and manipulate life at the molecular level. While this opens up incredible possibilities for medicine and agriculture, it also creates new risks. A lab leak, a bioterrorist attack, or a genetically engineered pathogen could create a disease far deadlier than anything nature has produced. Even worse, advances in synthetic biology mean that designer pandemics could be tailored to target specific genetic markers, making biological warfare both possible and potentially undetectable until it's too late. Pandemics are not just about health. They can collapse economies, erode trust in institutions, and destabilize societies. Global systemic collapse. Finally, we must consider the possibility of systemic collapse, where multiple crises converge to bring down civilization. Economic inequality, environmental degradation, misinformation, and political polarization are all stressors on the global system. Individually, they may seem manageable. Together, they could overwhelm the structures that hold society together. History shows that complex systems tend to collapse suddenly, not because of a single cause, but because of interconnected vulnerabilities. We may not survive the next century not because of a single disaster, but because of many slow ones converging at once. Scientific perspectives on risk assessment. Assessing existential risk is difficult, not because scientists lack data, but because many of these threats are unprecedented, complex, and hard to quantify. However, researchers have developed frameworks to estimate probabilities and guide policy. The Cambridge Centre for the Study of Existential Risk, CSER, the Future of Humanity Institute at Oxford, and the Machine Intelligence Research Institute, MIRI, are among the organizations working to understand and mitigate these dangers. One approach is expected value theory, which multiplies the likelihood of a risk by its potential impact. Even low probability events become significant when multiplied by infinite stakes, like the extinction of our species. Another method is scenario analysis, where experts model different futures based on current trends and interventions. These models help identify tipping points, early warnings, and resilience strategies. Yet despite growing awareness, funding and political attention remain minimal compared to the scale of the threat. Psychological barriers to action. Why do we ignore these dangers? There are several psychological reasons. First, existential risks are abstract. Unlike personal threats, illness, poverty, violence, they feel distant and intangible. Our brains evolved to react to immediate danger, not slow-moving global threats. Second, risk perception is distorted. We fear terrorism more than climate change, plane crashes more than heart disease. Yet statistically, the latter are far more likely to kill us. Third, groupthink and denial play a role. When institutions or cultures deny the severity of a threat, individuals follow suit, often out of fear, identity, or short-term interest. Fourth, optimism bias leads us to believe that disaster won't happen to us. We assume someone else will solve the problem, or that technology will save us in time. Together, these mental shortcuts make it easy to ignore the most important questions of our time. The long now, what remains when we're gone? Imagine a world without us, not in the dramatic sense of fire and war, but in the quiet, slow fading of all that we once were. There are no more cities, no more lights in the night sky, no more voices echoing through the halls of power or the streets of our great metropolises. The earth turns as it always has. The wind blows across empty plains. Rivers carve new paths through forgotten lands. Forests reclaim the ruins of human civilization. And yet, no one is there to witness it. This is not a nightmare. It is not a warning. It is simply a possibility. One that has played out countless times before in the long, silent history of the planet. Because extinction is not unique to us. It is the fate of nearly every species that has ever lived. But what, if anything, will remain of us? What, if anything, will be left behind? And if we vanish, does it matter? The impermanence of civilizations. Let's begin with what we know. Civilizations rise and fall. We look at the ruins of Rome, the crumbling temples of Angkor Wat, the abandoned cities of the Maya, and we marvel at their grandeur. But we also recognize a deeper truth. No society lasts forever. Even the greatest empires, the British, the Mongol, the Egyptian, eventually faded. Some were conquered, some collapsed from within, some were lost to time, their languages and cultures forgotten. And if that is true of the past, then it is true of us. We may believe ourselves different, more advanced, more connected, more resilient. But history tells us that no civilization is immune to the forces of entropy, change, and decay. Even if we avoid war, disease, and environmental collapse, there is still the slow erosion of memory, the fading of culture, the loss of meaning, because even if we vanish, the universe will not mourn us, it will not remember us, it will simply continue the physical traces we leave behind. If we disappear tomorrow, what would remain? What would be left of our cities, our technology, our art? In the short term, the first few centuries, nature would begin its quiet reclamation. Vines would crawl over skyscrapers. Water would seep into subway tunnels. Roads would crack under the weight of roots and time. In 1,000 years, most of our buildings would be gone, reduced to rubble, buried under layers of sediment. In 10,000 years, even the largest monuments, the pyramids, the Great Wall, Mount Rushmore, would be worn down by wind, water, and time. In 1,000,000 years, almost nothing would remain, except perhaps one thing: the fossil record. If any future intelligence, alien or post-human, were to examine the layers of the Earth, they might find strange anomalies: a sudden spike in carbon isotopes, a thin layer of plastic embedded in rock, a scattering of metal alloys not found in nature. They might find evidence of a species that lived briefly, burned brightly, and then vanished. And if they were curious, they might wonder, who were these beings? What did they create? What did they dream? The digital and cultural legacy beyond the physical. What about our culture? Our music, our literature, our art, our science, all of it stored on fragile media. Hard drives degrade, paper yellows, servers shut down. Languages evolve, meanings shift. Even if we try to preserve our knowledge on satellites, on the moon, in deep underground vaults, eventually those too will fail, unless we actively maintain them, unless someone is there to read them. They will become unreadable, silent echoes in the dark. And yet some of us have tried. Projects like the Long Now Foundation, founded by Stuart Brand, and others, aim to think in terms of millennia, not years. They've built a 10,000-year clock, designed to tick once a year and chime once a century, as a symbol of long-term thinking. The Voyager Golden Record, launched aboard the Voyager spacecraft in 1977, contains sounds and images from Earth. A message in a bottle cast into the cosmic ocean, drifting between the stars, and the Arctic World Archive. A digital vault buried in permafrost in Svalbard preserves books, code, and cultural artifacts in hopes that someone, someday, might find them. These are not just archives. They are acts of hope, attempts to say, we were here, we mattered, we dreamed of being remembered. The psychological and philosophical meaning of legacy. Why do we care about being remembered? Why do we write books, build monuments, name stars, and plant trees we'll never see grow? Because we are aware of our own impermanence. Because we are conscious beings, aware of time, aware of death, and longing to leave something behind. This is the essence of legacy. It is not just about survival. It is about meaning. Even if we vanish, even if no one reads our words or sees our art, the act of creating, of loving, of thinking, of feeling still matters, because meaning is not dependent on permanence. It is dependent on presence, on experience, on the simple truth that we were alive, and that we tried. The cosmic perspective widened the lens. From the point of view of the universe, we are a flicker, a species that evolved on a small, blue planet orbiting an unremarkable star in a vast galaxy. We have only existed for a few 100,000 years, a blink in cosmic time, and even if we survive for 1,000,000 more, we will still be a brief chapter in the long story of life on Earth. But that does not diminish our significance, because meaning is not about scale, it is about depth, about the richness of a single moment, about the way a child laughs, the way two people fall in love, the way a scientist sees a pattern no one else has seen. These things do not need eternity to be meaningful. They are meaningful because they are fleeting, because they are real. The possibility of renewal, even if we vanish, life may go on. Evolution does not stop with us. Another species may rise not in our image, not with our technology, but with its own form of intelligence, its own dreams, its own stories, and perhaps, in some distant future, they too will look up at the stars and wonder. If they are alone, perhaps they will find our bones, our ruins, our artifacts, and ask, who were these beings? What did they want? Did they leave? Or did they simply become something else? The peace in impermanence as we come to the end of this journey. Let us sit with the silence. Let us accept that nothing lasts forever, and that this is not a tragedy, because impermanence is not the enemy of meaning. It is its foundation. It is what makes every breath precious, every sunrise beautiful, every moment worth living. We may not be here forever, but we are here now, and that is enough. Drifting toward sleep now, let your thoughts slow, let your mind relax. Feel the weight of time settle gently around you, and as the stars watch silently from above, let yourself slip into sleep. Good night,